Okay, part two of our discussion on instantaneous rate of change is centered on something called the difference quotient. The difference quotient is just a rearranged version of the formula you use to calculate an average rate of change. The average rate of change calculation that we did was the one that looked like slope. It was just y2 minus y1 over x2 minus x1. Or using function notation, it's f at x2 minus f at x1 divided by x2 minus x1. Instead, what you can do is you can use a simplified version of the equation. Some people say it's simplified, but other people don't agree that it is actually simplified. But what it does is it takes this difference, x2 minus x1, and calls it h. H is the difference. And the reason it's called the difference quotient is because it's a quotient, two terms or two expressions being divided, and the bottom is the denominator is the difference between the x's. So they define the difference, x2 minus x1, as h. And then they write x2 in function notation as whatever the original x was, x1, plus the difference. So if your difference is 1 and your first point was 1, this would read f at 2 minus f at 1 divided by 1, because 2 minus 1 is 1. The difference is 1. That's how the difference quotient works. It sounds kind of confusing, but the reason I'm showing it to you now is because it comes up in calculus, and you'll get to see how this matches up with the first principles definition of a derivative, which is something you're going to learn about in calculus. So getting used to that terminology now would help you next term. It's also a part of our curriculum, so you get to see it now. So how do we use the difference quotient? Well, I have an example here, and we're going to use the difference quotient to find an instantaneous rate of change, or estimate an instantaneous rate of change. So it says the volume of a cubic crystal grown in a laboratory can be modeled by volume of x equals x cubed, where x is the side length in centimeters. Estimate the instantaneous rate of change with the side length of 5 centimeters. Okay, this is obviously a cube. It says cubic crystal because the volume is x cubed, and we want to figure out how quickly it's growing when the side length is 5 centimeters. So it suggests we use a preceding increment of negative 0.01 and a following increment of 0.01. What that translates to is, remember when I said to pick a really small interval to the left and to the right of where you're looking for your instantaneous rate of change? Preceding means before 5. So that just means that the range we're looking at is from 4.99 to 5. A preceding increment of negative 0.01 is the same as saying this. We're looking between 4.99 and 5. A following increment just means that we're looking at that interval. Okay? So, to use the difference quotient, we need to figure out what the function would be at a plus h. Well, what's a? A is where you're looking for your instantaneous rate of change. We're looking for an instantaneous rate of change when the side length equals 5. So a is 5. So we need to know for our first interval what the function is at 5. That's this term. We need to know what the function is at 5 plus our preceding increment of negative 0.01. And we need to know what h is. H is our preceding increment. This is h. So if we can figure out all three of these pieces, we can just plug them into our difference quotient, and that will give you an average rate of change. So our AROC is equal to f at 4.99, which is 5 plus negative 0.01, minus f at 5 divided by h, which is negative 0.01. So what is f at 4.99? And by f, I really should have been using v, but it would take a lot to white it out now, so please maybe use v. I guess f is okay because I'm trying to match the notation here from the difference quotient, so let's stick with f. Save me some work. So what is f at 5? Well, f at 5 just means plug 5 in for x, and that would be 5 cubed. And what would this be? Well, it would be 4.99 cubed. So 4.99 cubed minus 5 cubed divided by negative 0.01. And if we punch that into our calculator, we get approximately 74.85 centimeters cubed volume, because that's what the top is, centimeters cubed, and the side length h is in centimeters, so it's centimeters cubed per centimeter. That's the rate with which our cubic crystal is growing from the left side, or just before 5. Just after 5, it would be a similar setup. We know the function at 5 is just 5 cubed. We need also the f at a plus h, our new h, our following increment is 0.01. So we also need f at 5.01, which would be 5.01 cubed. Our average rate of change from the right side is just f at a plus h, which is 5.01, minus f at 5, divided by h, which is 0.01. And that again is 5.01 cubed minus 5 cubed divided by 0.01, which if we plug that into our calculator, we get 75.15 centimeters cubed per centimeter. So what you can see here, approximately equal to, what you can see here is from the left side, or preceding, we have a slope of our secant that is 74.85. So we can say our average rate of change before 5 was 74.85. Our average rate of change after 5 was 75.15. And I think you can see where this might level out to, or balance out to, or average out to if we were to add them and divide by 2. And that's what we'll do to estimate our IROC. So we'll say that our IROC, I'm going to write it down here, IROC is approximately equal to our mean, which means average, AROC, one from the left, one from the right. The one from the right side, our following increment, was 75.15. From the left, our preceding was 74.85. Average means add them up and divide by 2, because we have 2 terms. We get 75 centimeters cubed per centimeter. So this is a concluding statement that's accurate for our estimation of our instantaneous rate of change. It's equal approximately to, or we're estimating it by taking 2 AROCs and adding them up and dividing them by 2. Our 2 AROCs, one before 5, so our interval's from 4.99 to 5, and one after 5, our interval from 5 to 5.01. Okay, thanks for watching, and I'll see you next time.